locked and we have good to send that command. We have 31 minutes and 32 seconds for our support. Go for status buffer dump.
Since the retirement of the space shuttle, the engineering team is absolutely critical for Hubble. It always has been.
Without the shuttle going up to replace any equipment failures that we have to make do with what we have. What we really are concentrating on is just keeping the telescope working and keep the science going.
And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
My name is Mike Wenz, and I'm the lead systems engineer for what's known as the Optical Telescope Assembly of the Hubble Space Telescope. I'm in charge of what's known as defined guidance sensors. These are the instruments that actually help Hubble do the exquisite and precise pointing that it does. Right now we're getting ready to perform an observation. The telescope is going to be trying to go to acquire some guide stars in just a few minutes here. The stock is the Space Telescope Operations Control Center, where we send commands to the spacecraft. On a daily basis, we have to send up what's known as command loads.
Accepted. DCMR is good. Step 3 is complete.
Because the computers on Hubble are very old and they have very little memory, in fact, most of your memory sticks today are 20, 30, 100 times bigger than Hubble, we have to send up essentially a load of all the commands Hubble's going to be doing for the next 24 hours.
On a routine basis, we always keep 24 hours of instructions on board, so it's routinely updating for the new sequence 24 hours in advance.
We'll start with doing our premise uplink.
Hubble is always working, it's always doing something, it's always doing some sort of observation or calibration or getting ready for the next task.
We'll be locked on our forward at 14:33:17.
Hubble is truly a 24/7, 365-day-a-year instrument, so Hubble can keep on going. It never stops.
And we are configured. It's been verified.
Now we do have to, because of this low Earth orbit we're in, the actual observations, when we're taking a picture of something, or doing a science observation, we actually have to wait because sometimes the Earth gets in the way. So we have to pause, wait until the Earth gets out of the way as we go back around and start the observation back up.
You have constraints. You don't want the optics pointing at the sun, and you don't want the instruments to have their shutters open when you're looking at the Earth, because the Earth is bright for them. And then we have the South Atlantic Anomaly, the SAA, which is a portion of the Earth where we get proton hits that will affect the electronics in Hubble and can also affect the instruments in Hubble. And so we have to plan out very carefully our targets and observations. We have a timeline that's laid out to maximize the efficiency of it.
Hubble can actually take observations during day and night passes. Every 95 minutes, we go around the Earth. The batteries will charge from the solar rays during the day pass, and then at night, batteries power the observatory so we can continue observing. The scheduling with Hubble, we're trying to put it together as efficiently as possible, minimize our gaps. The goal is to constantly keep it busy.
We're constrained to a certain extent, but whenever we have visibility, we are observing.
The demand for use of the Hubble Space Telescope from scientists around the world is very high.
Hubble is at its most productive. It's got some of the best instruments that have ever been on board it. There's a very high demand. Hubble's performing exceptionally well.
2, 1, and liftoff of Space Shuttle Atlantis. A final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Since the final Space Shuttle servicing mission, we're using Hubble to get the best kind of science return we can from the suite of instruments that we have. So our focus now is on making sure we get the best science while it's still operating so well.
Luckily, at the end of the last servicing mission, we were actually left with a telescope in great condition, but Hubble is getting older and older. It's a very old telescope.
Now, 10 years after the last servicing mission, we can't rely upon servicing missions to fix things, so we have to rely upon our own ingenuity to be able to figure out if something does fail, what are the alternative paths that we have.
For the telescope to keep giving us this peak science, we need lots of things to be working together very well on the telescope. We need a pointing accuracy system that is outstanding and keeping that whole system healthy and functioning so that we can point Hubble very accurately even while it's whizzing around Earth in its orbit.
For the telescope to be able to do the science it needs to do, we have to hold it very, very steady. There is actually a little bit of motion. I mean, it's hard. We're zooming around the Earth at 17,000 miles an hour, so it's hard to hold the telescope perfectly like that. The gyros are working really good.
The gyroscopes can sense motion in each direction. And so because of the gyroscopes that we have on board and how sensitive they are in terms of sensing motion, that we can keep our cameras steady.
Gyros are very good at measuring these very small rates. The fine guidance sensors are actually sort of used, I always like to describe it as backseat drivers. And they constantly tap on the gyro's shoulders, it's about once a second. And they keep saying, turn left, a little bit more right, a little bit left, a little bit right. I mean, it must be driving the gyros nuts. So the fine guidance sensors allow you that really fine control, but actually it's the gyroscopes driving the telescope. And they're doing a perfectly good job here. Everything looks good, our star is the right brightness. The reason that is because we need to make sure we have the correct guide stars. One of the things we look at is the brightnesses, and that's what we're measuring here. Those are about right for what the stars were. But also, we wanted to make sure they were exactly as far apart as we thought they were going to be. And it did. It did a check, and it passed a very, very tight tolerance check to make sure that those were the right stars. So we know we're locked up on the stars. We got a good lock here. The gyroscopes are very critical because to be able to move from one position to another position, the gyroscopes are the only thing that can tell us how we can do that. We have 6 gyroscopes on board Hubble. Currently, 3 of them are still working. And 3 is sort of what people used to think of as the minimum number, but we have developed a science mode where we only need 1 gyro.
A big part of our job is to make sure that we can extend the life of Hubble and continue doing the high-performance science that we're doing for many more years.
And what we've done is we've gone through all the critical components of Hubble and said, how can we potentially make them last longer, as you might do with your own car as it's getting more miles on it. The gyroscopes have been our most problematic piece of hardware, so I helped lead an effort to develop a 2-gyro science mode. And we were able to use that mode on orbit and be able to perform science. And then learning from that, we actually developed a 1-gyro science mode that we've been able to test on orbit, but we haven't been called on to use. But in the end, possibly 5 to 10 to 15 years from now, when we're down to potentially our last gyroscope, that is the mode we will be in. Before we do anything on orbit for the first time, we have to test it out on the ground. And we're very lucky to have what we call the VEST, the Vehicle Electrical System Test Facility. And the key with the Vehicle Electrical System Test Facility is it's an exact copy of the main part of the telescope where all the electronics are. And it has the mechanical bays, it has the computers, the electronic boxes installed in there, and it has the cables and harnesses in there. And in fact, when we were building the VEST, we had the quality engineers came to us and said, you're not doing these cables exactly the way you should be doing them. You know, we've got better standards now. And our thing was, we're trying to build a copy of what we have on orbit. And so what you have in the VEST is an exact electrical copy of the Hubble Space Telescope. Every orbit as we come around the Earth, to be able to get our attitude correct, to get ourselves steady and locked on. The fine guidance sensors and the gyroscopes are key to that. And that's why those are the 2 of the subsystems that are on the top of our list as far as having contingency plans for and monitoring the health and safety of those and making sure we have them in peak performance. When something fails on Hubble, or we have an anomaly, something we don't understand, one of my jobs is to bring together the experts, which may be a thermal engineer, a mechanical engineer, an electrical engineer, a software engineer, all these different people. And we'll say, you know, how do we deal with this issue? And how can we work around it and return back to peak science? What you do is you come up with a list of what is available to you on the telescope in terms of potential. I could close this relay or open that relay or turn on this box. And I am continually amazed. You have a telescope on orbit that you can't even see. I mean, all you're doing is looking at the data coming down to you from the ground. These experts are able to use their ingenuity and come up with ways to continue to operate Hubble. And everything looks excellent, and we have no reason not to expect that Hubble will last until the late 2020s and beyond.
I personally am extremely grateful to the Hubble operations team, these people who work day and night to keep Hubble operating, providing exquisite science return, giving us the information that we need to know how Hubble's doing. Is it doing the kind of accurate pointing that we need? Is it getting the sensitivity in the various wavelengths of light in the various instruments that we need to have to do the science? Are we able to calibrate those observations in an accurate way. We couldn't do any of those scientific analyses if we didn't have this team of operations experts behind the scenes making sure that the details of Hubble's technical operations are being monitored, being handled, being managed, being planned in a near perfect way. Because the Hubble Space Telescope is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe.
One of the primary things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space to be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is, as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky. And they figured out a way to use Hubble in a vast tracking mode that enabled us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. So we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. You start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope so we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments, and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond.
Go for status buffer dump.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields. Looking out into space and collecting light, sometimes for many days, these deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. There's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies, the way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to the next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we fly today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.